Direct substitution. That's what we're going to focus on anytime I ask you to do a limit problem. If I give you a limit problem and I ask you to evaluate the limit without looking at a picture and without doing a table of values, if I just give you a problem and ask you to evaluate the limit, I want you to always start with the direct substitution property. Plug in whatever x is and see if you get an answer. If you substitute in whatever x is and you get out a number like 39, well, that's what our limit is. That's what we approach as we approach that x value, 39. Or if you substitute it in and you get 5/2, well, as we approach x equals a, then we're going to be together at 5/2. So the very easiest thing you can do anytime I ask you to evaluate a limit problem is to direct substitute. Okay, but what happens, unfortunately, when direct substitution gives you an answer that's kind of funky? Well, let's talk about it. When you direct substitute and you end up getting the answer 0/0, so you don't actually get a number like 39 or 5/2, you end up getting 0/0. What that means is that my limit does exist. What happens is there's really a hole in our graph. Do you remember when we factored and we canceled out a factor from the numerator and the denominator? What that means, or if you were to do it algebraically or direct substitution, you would have ended up getting a 0/0. That means there's a hole. So anytime I direct substitute and I get 0/0, that means there's a hole in my graph. But remember, just because there's a hole doesn't mean that my limit doesn't exist. Remember Starbucks? Just because Starbucks is closed doesn't mean we can't hang out there until they open. So even though we get 0/0, doesn't mean that my limit doesn't exist. It does exist. We just have to somehow figure out where our path is, even though there's a hole in our way. So what we're going to try to do, really, is kind of get rid of that hole. We're going to try to simplify and then resubstitute. So a couple different things we can do to simplify is by factoring. If we can factor the numerator, factor the denominator, and get rid of that hole, cancel out those factors on top and bottom, and then we can try to resubstitute and see where our path is at. Now, if factoring doesn't work, a second method is rationalizing. We can rationalize the numerator and figure out where the hole is then, and then get rid of it and resubstitute. So factoring and rationalizing are two of the main methods we're going to use to simplify, to get rid of the hole and figure out where we're at and see if we're together at Starbucks, even though it's closed. Now, if you do your direct substitution and you get a number over 0, any number besides 0, any number over 0, remember 0 under the line is undefined in math, and so our limit doesn't exist. What that means, remember, is there's a vertical asymptote in your graph. If there's a vertical asymptote in your graph and you approach that vertical asymptote, well, then our limit doesn't exist. Well, wait a second, we don't want to stop there. Remember, if we hit a vertical asymptote, there's only 3 options. We're either going to go up, we're going to go down, or we're going to go opposite, and then you can say that your limit truly doesn't exist. But if you hit that vertical asymptote and from the left and the right, both of your graphs go up, we're going to really say that our answer is approaching positive infinity. If both of your sides go down, you're going to approach negative infinity. But you have to know the difference between hitting a hole versus a vertical asymptote. Let's practice a few. Look at example 6 with me. Find the limit as x approaches 2, and it gives us this function. Remember, anytime I ask you to evaluate a limit, that's the very first thing that you should always try. Direct substitution, right? So I want you to take this 2, and I want you to substitute it in wherever you see an x. When I substitute in a 2, I have 2 squared, which is 4. 4 plus 2 is 6. 6 minus 6 is 0. And when I substitute in a 2 to my denominator, I ended up also getting a 0. So what does that mean if I have a 0/0? What's happening in our graph if I have a 0/0? Yeah, a hole, right? And so now I know there's a hole there. But just because there's a hole, remember, doesn't mean that the limit doesn't exist. We just have to somehow ignore the hole for a second and figure out where we're at and see if we're together. So what are some ways to get rid of the hole? Well, remember, we can factor or we can rationalize. Let's go ahead and factor this one. I would like you to factor that numerator for me. Hopefully you know how to factor. You've been doing that a lot back in your algebra classes. We need to figure out numbers that multiply to -6, that when you add them together you get +1. So I factor the numerator into an x plus 3 times an x minus 2. And then my denominator is still that x minus 2. You notice that I've followed my limit down into my problem. So I don't have floating problems. I'm still doing a limit as x approaches 2. So please make sure that you're practicing your good notation. You're being organized and neat and clear so you don't make any mistakes. So now we're doing the limit as x approaches 2 of a factored problem. And if you notice, I have an x minus 2 on the top and an x minus 2 on the bottom. I can reduce those factors. And when I schmear, what did I just do? Well, I just got rid of the hole, right? I just plugged up the hole that was at x equals 2. And that's why when I tried to substitute in a 2, I didn't get an actual answer. But now that I've gotten rid of the hole, I now have a new equation that says the limit as x approaches 2 of x plus 3. Now this graph and my original graph are the same exact picture, the same exact path. The only difference is on my x plus 3 graph, there is no more hole. We've ignored the hole, we've plugged up the hole, and now let's figure out where we're at. So on this new path, the same exact path as before, now that we've plugged up the hole, what happens as we approach x equals 2? Well, now let's do our direct substitution, now that we've gotten rid of the hole, and figure out where we're at. If I substitute in a 2, didn't you get 5? So I can say that the limit of my original problem, x squared plus x minus 6 over x minus 2, is 5. Let's do another one. Find the limit as x approaches negative 3 of this function. The very first thing, always, 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 that you should try to do is direct substitute. Because if you plug in a negative 3 and you get a number, well, then you're done. That is your limit, right? Let's plug in negative 3. When I substitute a negative 3, and be careful using your parentheses, I have a negative 3 squared. That's a negative 3 times another negative 3. That's a positive 9. And then I have minus a negative 3. That's a positive 3. And then minus 12. I ended up getting 0 in the numerator and 0 in the denominator. So now that I have a 0 over 0, what's happening in my graph then at x equals negative 3? Yeah, there's a hole, right? But just because there's a hole doesn't mean that my limit doesn't exist. Let's get rid of that hole. Let's plug up the hole for a second and figure out where we're at on our path. Let's do that by factoring. So factor your numerator, factor your denominator, and let's see if we can get rid of that hole. Numbers that multiply to negative 12, that add to give me negative 1. I got x minus 4 and x plus 3 in my numerator. My denominator is still just an x plus 3. But what do you notice? Schmear, we just got rid of that hole, right? We just got rid of that hole at x equals negative 3, and so now I can focus on just this part of the path that doesn't have a hole on it. I have the limit as x approaches negative 3 of x minus 4. I can figure out where we're at as we approach negative 3 by plugging in a negative 3 now, because I don't have a hole, and I have negative 3 minus 4, which is negative 7. So my limit approaches negative 7. All right, let's do one more. The limit as x approaches 1 of x squared minus 1 over x minus 1. The very first thing you're going to do, direct substitute, right? 1 squared is 1, 1 minus 1 is 0, 1 minus 1 is 0. I got 0 over 0, which means I have a hole. And just because there's a hole, though, doesn't mean that the limit doesn't exist. So let's get rid of that hole. Let's redo our direct substitution and figure out where we're at, even though Starbucks is closed, right? All right, let's factor the numerator. You should recognize that as a difference of squares. I should be able to factor that x squared minus 1 into an x minus 1 and an x plus 1. I notice that I have a factor on the top and a factor on the bottom. Schmear. I've just plugged up that hole, and now I can figure out where we're at as x approaches 1. Plugging in my 1, 1 plus 1 is 2, and so I can say that my limit approaches 2. There's a hole there at x equals 1, 2, but we can still get really close to each other and hang out until Starbucks is closed. So the graph of this one might look something like this. At x equals 1, 2, there's a hole, but as we come close to that hole, we are together at 2.